Now that you have some familiarity with the magnetic field produced by a line of current, let's put the line of current into a loop. Little extrapolation there. So our loop is going to be centered at the origin, and current is going to be in circulating the direction shown. So around this way. What's the magnetic field produced at point P? The radius of the loop is A, and our radius or distance from point on the loop to P is R, which is square root of A squared plus X squared. And we have dl. So here's dl, which is in the direction of the current. All right, so we're going to integrate. We're going to be integrating around in this direction, this dl, as you can imagine. So we have a little unit vector r here at this location. And so we're going to apply, to analyze this, the Biot-Savart formulation, which gives us a dB. Now, we should be able to figure out what direction all this is. dl cross r, if you cross this vector into this vector with your right hand, do that in your mind's eye right now, what is the magnetic field direction at point P? So if you're doing that correctly, here's our angle, theta. You should get a dB in this direction. It doesn't look very dB-ish. It's pretty long, but that's of no consequence for our analysis here. So this angle theta is the same as it was over here. All right. So dB is Biot-Savart formulation, mu 0 I over 4 pi dl over r squared. Now, it's mu 0 I over 4 pi dl over x squared plus a squared. That's r squared. Now we have a dBx and we have dBy. Because of symmetry, if you think of, we're going to analyze every little dl along here, you'll notice you can kind of almost visualize this dBy. For every point over here, the dBy is going to be this way. So every point has a corresponding point, and they all cancel. So we get no B field in the y direction at point P. So we're going to worry about x. dB in the x, of course, is dB cosine of theta. dB cosine of the angle, which is mu 0 I over 4 pi dl over x squared plus a squared. Cosine of theta, if you look at this one, this angle, cosine is adjacent. That's a over hypotenuse. So a over x squared plus a squared, square root thereof. And now, magnetic field in the x direction. Let's integrate. Bring out the constants. This is a constant, of course. But what's so nice about this circle and the symmetry is that this is a constant as well. Yes. So we're going to integrate dl. These are all constant because the distance here along here is the same. This x is the same value and a is a constant, and we're everywhere at radius a. All right. So integrate dl and we got 2 pi r, but r is a. So that gives us bx mu 0 I a squared, because, well, we have this a and this a, and the 2 pi, makes pi go away and makes 4 into a 2, and this is to the 3 halves, and we multiply it by n because we have n loops. So there's the B field produced by a loop of current in the x direction, and obviously it's proportional to the number of turns, the current, the radius squared, but then of course it's inversely related to that as well, to the 3 halves power, so that's not immediately obvious what that looks like. And in any case, there it is, and now let's look at how that would graph. So now let's graph the B field of that magnetic loop, and we only have an intensity or a non-zero value in the x direction. And here's the formula again. I should have mentioned in the last slide when we looked at what bx is related to. It's inversely proportional to x squared, and that's to the 3 halves power. So obviously in the x direction for a given a, it trails off quite rapidly. In fact, to the inverse third power. Now, the maximum is obviously in the center then, or at 0, because x is here in the denominator and it's 0. So the value is, for the maximum, mu 0 ni a squared over 2a squared to the 3/2 power, which simplifies down to mu 0 ni over 2a. So notice that the maximum B field is inversely proportional to A. All right, so when we graph this out, we get something that looks like this. Maximum in the center, trails off very rapidly in both directions. This is a magnetic dipole. We have a loop, and in the x direction, we have an intensity of magnetic field that trails off like this. It acts like a little bar magnet, tiny little bar magnet. The magnetic dipole then is, we can consider that a source of magnetic field, very common. Remember mu, the magnetic dipole moment, not the permeability, mu 0, but mu is Ia, and that's I pi a squared. So mu total, multiply that by n, the number of loops, and we get this. Oh, look at the denominator of this equation. So here it is again. And since ni pi a squared is the magnetic dipole moment, we have that expressed here. So we can write it like this. We divide by pi, then mu 0 mu. Remember, these are two different quantities: permeability, dipole moment, magnetic dipole moment. And even though it looks like the magnetic field in the x direction is proportional then to the magnetic dipole moment, remember it's related to a squared, and you see a squared in the denominator to the 3/2 power. So even though you could say it's proportional to mu in this expression, it actually diminishes as mu gets bigger. Since it's dependent on A gets bigger in such a way that the larger the loop, the smaller the magnetic field is for a given x along the x-axis. Well, we have now produced the background necessary to investigate Amperes Law, which will be the topic of the next video.